Assalamualaikum and a very good day. So today our group would like to present about our project which is FEA Finite Element Analysis of Byte Frame. So our lecturer is Dr. Wayano Sabtu Widodo and we are from 3 BMKV section 1 stroke 2. So I would like to introduce first our group member which is first Farihin bin Muhammad Fuad and myself, I'm Hafidz bin Amrizan, and the other group member which is Ishraq Wajdi bin Shauqi, and also Muhammad Arif Danial bin Azaman. So first we go through introduction. To make bicycle frame strong, durable, and high performing, designers focus on creating solid structures and use finite element analysis to test how frames handle different stresses. So we will use finite element analysis to analyze and to identify which area will experience the height stress and also will experience the deformation based on three conditions that we choose, which is flare road, which is or stationary type, inclining the road and also declining the road. So from there, we will do analysis to identify which part is experience the height stress and height deformation. Unlike earlier research that mostly improved suspension system in car and motorcycle, this project emphasized innovative bicycle frame design. So, like I said earlier, our project is focused on the bike frame design and the analysis of the bike frame that we have designed. So the goal is to find the best balance between strength, weight, comfort to ensure the bike is safe and enjoyable to ride. So for this project, we focus on the commuter bike, which is the bike that usually people use for leisure ride. So for this commuter bike, we need to also include the economic of the design to give the comfortness to the cyclists or riders. So this approach allows for smarter, more efficient bicycle design without costly physical prototype. So by using the finite element analysis, we do not have to spend our money to do the prototype and test the design that we have designed earlier. So we move on to the problem statement. So in our project, we have identified three problem statements, which is first, balancing critical design factors. Bicycle frame design must carefully balance minimizing weight, maximizing lateral stiffness, ensuring strength, and achieving vertical compliance. This factor directly affect performance, safety, and also rider comfort. But traditional methods often struggles to optimize all simultaneously. So the next problem statement is challenge of real-world loading conditions. Frame face complex and variable loads during actual use, making design difficult. Current approach lack a systematic way to analyze and optimize frames under diverse loading scenarios, leading to compromise in strength or weight. And the last one is FEA driver integrated optimization. This project applies finite element analysis to simulate multiple load cases, identify stress critical areas, and refine the frame structures. The goal is to develop a frame that exceeds current standards in weight efficiency, strength, stiffness, and compliance, resulting in safer, more reliable, and higher performance bicycle. So we move on to our objective of our project. In our project, we have identified and listed down three objectives that we aim to achieve at the end of our project. The first one is to design a 3D model of a bicycle frame tailored for a specific type of bike, ensuring it meets the requirement for weight, strength, stiffness, and compliance. The second one is to develop, verify, and validate a finite element model of the design bike frame, ensuring accuracy in simulating real-world conditions. And the third one is to perform finite element analysis (FEA) to identify critical stress and deformation areas under various loading conditions and suggest design improvement based on the finding. So this is three objectives that we have highlighted in our project. So we move on to the next part, which is the scope of project. So in the scope of project, we divide it into five parts, which is first, design and modeling of bicycle frame. So in design and modeling of bicycle frame, we focus on identify and choose a specific type of bicycle for which frame will be designed. And the second one is to create a detailed 3D model of bicycle frame including dimension and geometric features necessary for the specific type of bicycle. And the last one is to choose appropriate material for the frame. For this project, we use a titanium alloy because it has a high strength to weight ratio, fatigue resistance, and also corrosion resistance. So the second one, we focus on finite element analysis. So in finite element analysis, we put limitation on to develop a finite element model of the design bicycle frame, including meshing, element section, and defining boundary conditions. And the next one is to stimulate various boundary conditions such as flat road or in a static condition, incline road, and decline road to evaluate the frame's response. And the last one is to analyze the maximum and minimum stress as well as total deformation to identify critical stress points and area prone to fail. So the third one is safety and performance optimization. So in safety and performance optimization, we focus on to calculate and analyze the safety factors for different loading conditions to ensure the frame structural integrity and safety. And the next one is to suggest and implement design improvement based on finite element and analysis findings to enhance the frame strength, stiffness, and compliance while maintaining low weight. And the fourth one is documentation and reporting. So in documentation and reporting, we focus on to document and present the finding of FEA simulation, including stress, distribution, deformation, and safety factors, and also to provide comprehensive recommendation for frame design improvement to meet and exceed performance standard. The last one is about presentation. So after we do all the things that we do in project, we will develop clear and concise presentation including slides and visual aids that summarize the project objective, methodology, result, and conclusion. So that is our scope of project. So that's all from me. Thank you.
So this is a part of the flowchart. So the simulation process is a method approach to design validation. It begins with define a clear objective and problem statement, followed by a literature review to ensure the design aligns with existing knowledge. If it doesn't, the process will stop. Next, the initial sketch lead to a detailed 3D model and material selection (FEA). Then assess structural integrity. This involves mesh the 3D model and applying boundary condition load to the simulate real-world condition. FEA provide data on stress, deformation, strength, and safety factor, identify potential weakness and refinement. Finally, simulation results are validated. If they meet the standards, the project is successful. Otherwise, the design is iterated and improved until it meets all the performance criteria. This systematic approach enhances the efficiency and minimizes risk, leads to a robust design. So this part is about the literature review finding. So in this literature, we have a five term that we find to our project. So the first term is about the material selection. Second term is structural design, geometric consideration, and stress and deformation analysis, and FEA to uh, to elaborate our project about the bicycle bike frame. So in the part of the methodology, we have three terms to elaborate our bicycle bike frame project. So first is about generate the model. So we will generate the model bicycle frame using SolidWorks and we'll export to the NCs to make the analysis for our bicycle bike frame. So second is run simulation on bike frame. So to get the geometrical model, material properties, meshing, element type, and bordering condition for three type, which is flat type, flat rod impact, declining impact, and inclining impact of three fault, which is seats, handlebar, and pedal. So lastly about the method is our result and discussion. So the result and discussion after the simulation done will be discussed. Um, we will recommend or suggest about the next finite element analysis. So the 3D drawing of the bike frame that we compile it. So the design concept one is the first project we use to present to doctor, but it might doctor say it's simple, so we elaborate more for the three design concept. So the design concept of two have been handlebar frame is such much lower, so we made a force more implied into that. So in design concept 3, we choose it because it's more structural and more complexity. So after discuss for group member, we choose design concept 3 to make a simulation for our project bicycle back frame. So this part is about a technical drawing of bike frame. There we make a dimension of all the aspect of this bicycle bike frame that we choose. So we elaborate, we align with the literature review the journal previous. So we align with that. So we get this current result.
Assalamualaikum everyone. My name is Muhammad Arif Danial and I will continue to present about the result of finite element analysis FEA conducted on the bicycle frame. The aim was to simulate how the bike frame behave under different riding conditions and evaluate its structural integrity. We analyzed the three cases, riding on a flat road, in an inclining road and declining road. For the first one, the flat road impact, let's start with the first scenario, flat road impact. In this case, we apply a force of 1010 Newton vertically on the frames to simulate a rudder on level terrain. On the left, you can see where the force was applied and how the frame was supported. On the right, the deformation plot shows displacement in different regions of the frame. Arrows in red represent higher deformation, while blue indicates minimal movement. The analysis found a maximum stress of 2.813 megapascal and a safety factor of 3.8061, indicating the frame performed reasonably well under this condition. And then the second one is the inclining road impact. The inclining road impact is the next we tested the bike frame on an inclining road, which is here the applied force was slightly higher at 1193.63 Newton, simulating the additional effort when climbing uphill. The left image again shows force and support locations, while the right image shows total deformation. Interestingly, the maximum stress in this case was only 0.38759 megapascal, which is lower than in the flat road scenario, and the safety factor was at 2.3994 times 10 to the power of 9. This happens because uphill riding aligns most forces along the length of the frame tubes, creating action loads that are easier for the structure to handle. And finally, we have the declining road simulation where the applied force was 1120 Newton. As shown in the formation plot, there is a significant increase in displacement, especially near the joints and the front triangle of the frame. The maximum stress jumped to 36.863 megapascal, and the safety factor is 2.5229 times 10 to the power of 7, making this condition the most critical for potential failure. The higher stress is due to bending moments and braking forces during downhill riding, which create more localized stress concentration in the frame. Lastly, for the result and the discussion, to summarize this table highlights the critical results for each condition. On the flat road, the frame performed adequately with moderate stress. On the inclining road, despite the higher force, the stress remained very low due to efficient force distribution along the frame. And however, on the declining road, the stress increased drastically. This suggests that downhill riding is the most demanding on the frame and possess the greatest risk of structural failure, especially under high impact or braking forces. Overall, this simulation emphasized the importance of reinforcing critical areas like the joints and front triangle to improve safety under real-world downhill conditions. That's all from me. Uh, I will pass to the next presenter.
Hi, my name is Ishraq Wajdi bin Shauqi and I'll present for the flat road impact. For the max stress for the flat road impact, the maximum equivalence for von Mises stress is equal to 2.8138 MPa, while the minimum equivalent is 4.211 times 10 to the power of negative 5 MPa. On the right side is total deformation, which is the maximum total is equal to 0.005293 millimeter, while the minimum total deformation is 0 millimeter. And for the flat road impact, for safety factor, it shows that for force for 1010 Newton, the maximum safety factor is 2.2081 times 10 power of 13, while the minimum safety factor equal to 3.8061 times 10 the power of 3. For both calculation, for safety factor, the maximum stress that it can handle is 2.8138 MPa, and the result is 285.71. This shows that the bicycle is in the safe condition on the flat road surface. For inclining road impact, which is bicycle go up to hill, the max stress for the von Mises is 0.38759 MPa, while the minimum equivalent stress is 3.6481 times 10 the power of negative 8. The total deformation is maximum for the maximum is equal to 0.006116 millimeter, but the minimum total deformation is equal to 0 millimeter. As you can see, the stress on the right, it have the rate stress, which is critical stress or maximum stress between handle and seater. But the seater stress is quite an angle because we go up to the head. Safety factor for the inclining road impact. For force, we put 1193.63 Newton, and the maximum safety factor equal to 2.5942 times 10 equal the power of 60, and the minimum safety factor is equal to 2.3994 times 10 the power of 9. The calculation for safety factor for inclining road, we count it at 15 degree, and the maximum stress equal to 0.39759 MPa, and the formula for the safe factor is yield strength divided by maximum stress, and which is yield strength is 800 times 10 the power of 6, while the maximum strength is 0.39759 times 10 the power of 6. So the result for both for the formula is 2028.96. So as you can see, the figure show the blue color of the bike frame. So for the inclining road impact for 50 degree is safe. For the next is for declining road impact. The max stress for the declining road impact is 0.38756 MPa, while the minimum equivalent stress is 3.6481 times 10 the power of negative 8 MPa. So the total deformation for the declining road impacts, the maximum is 0.10169 mm, while minimum total deformation is 0 mm. As you can see, the stress only on the seater part, which is angle, for the declining road impact is only tip of the seat, while the following of the red color is yellow and turquoise. which is the stress is less and lesser. And for the safety factor for the declining road impact, 4 force equal to 1010 Newton, and the maximum safety factor is 2.2888 times 10 to the power of 11, while the minimum safety factor is 2.5229 times 10 to the power of 7. The calculation for safety factor is yield strength divided by maximum stress, which is 800 times 10 to the power of 6 divide 30 to 36.862 times 10 times 6. So the equal for the declining road impact is 21.7, and safe, and it's safe same as declining and flat inclining and flat road. For the conclusion, the purpose of the project is to improve the performance bicycle frame under heavy loads. The bicycle frame needs design improvements, especially by reinforcing certain areas. The main challenge is balancing weight reduction with enough stiffness and strength by fixing weak point and optimizing material use. The frame safety and durability can meet or exceed road cycling standards. This approach creates a stronger and more efficient bicycle frame.